We're going to start with a demonstration, so hopefully you're getting that copied down. And are we going here? Are we live? Ooh. Do you remember this? There we go. Do you remember this? We did this a while ago. So here's our original function, and this is original function, this is derivative function. This would have been helpful to review before the test yesterday, or maybe just before what we just did. I don't know. So as I move this point along, what does the derivative tell us about the original function? So again, here's the point. We're envisioning a tangent to that point, a tangent to the curve at that point. The y value of the same x value point on the derivative function is equal to the slope of the tangent. Fundamental calculus right there. If you're ever stuck on anything, go back to that. Remind yourself of that fundamental principle, right? So the tangent to the curve at this point would have a slope of about 5. Some people get confused and they start to think, well, the point on the derivative is decreasing. No, we don't care that the point on the derivative is decreasing. The fact that the derivative is positive tells me this point is increasing. That's what it tells us. Okay, again, fundamental stuff. So then we know we get to a turning point, and it changes from increasing to decreasing, and we have an x-intercept at the derivative. Okay, and the derivative function changes from positive to negative, hence why in a first derivative chart, we only care if it's positive or negative. Changes to positive. In this entire section of this function, I'm decreasing. That's where the derivative function is below the x-axis where it's negative. Okay, and then I change to increasing. So that's what we've seen before. What does that have to do with trigonometry? Here's our new one. So the way that we derived derivatives, like in how we calculate them before, we can't do that with trigonometry. It's not going to work. The way we came up with derivatives using limit properties, and we proved them, and power rule, product rule, and power of function rule, and quotient rule, all that stuff. Can't do that with trigonometry, unfortunately. So we're just going to kind of look and see by inspection what's happening here. So here's sine. This is the equation of this tangent line that you're looking at. So what is the slope right now? No? 1. Right? Y equals 1x. So this has a slope of 1, which means the derivative function would be where? It would be there at 1. Okay, I'm going to see what happens. We're increasing, right? On this function, we're increasing, so the derivative will be positive, but I'm getting a smaller slope, and then I have a slope of 0. So where would the derivative function be? It would be there. By the way, I don't want anybody to shout anything out. I want us all to do our own thinking. I'm going to ask some rhetorical questions. They're all rhetorical, meaning I'm not actually asking you, but you think about it. What happens after that point? We're decreasing, so where would the derivative function be? What's the slope here? Okay, you can answer that one. -1. Still decreasing. 0, where would the derivative function be? It would be there. Does anybody think they know what's going on yet? Some of you cheated and you looked it up, I know that. And then I return after a full cycle, we're back to a slope of 1. Let me go back over that. Look at this. Between pi by 2 and 3 pi by 2, I'm decreasing. So that's where the derivative function would be negative. Okay, that's hard. Let's try it with a point that you can actually follow. That was all visualization. That's hard. What if you can follow a point? See if you can figure out what that point is mapping out. So it started at 1. Now it's at 0. Now it's in the negatives because I'm decreasing. Now it's at -1. Now it's back to 0. Now it's back to 1. Anybody follow that? You think you know what's going on here? The only other thing I would say that's interesting to think about, in fact, I'm going to turn this off for this, is the slope. As I go back and forth here, the slope isn't of the tangent's not changing very much, is it? It's just wobbling a little bit back and forth. Would you agree with that? Slope of the tangent isn't changing very much. That means the derivative function isn't changing very much. What would that look like? But when I get to this peak, what's happening? in that same space, the slope of the tangent is changing a lot. Changing from positive to negative and just changing a lot. Like, look at that line, right? What would it look like for a function to be changing a lot? Okay. Let's turn this all on and see if we can figure out what's happening here. Catch everybody up. So now it's leaving a little path or tail as it goes. And I hope we can all see what function that is. And this seems like the easiest thing in the world. So the derivative of sine is? Now you can answer. Cosine. You see that? Derivative of sine is cosine. We'll do it one more time. If I just map out one cycle, doesn't that look like cosine? Interesting. Okay. Reset. Off. Get rid of that. Cosine. Now we're going to see what the derivative of cosine is. And you all think you're so smart. You already know what's going to happen here. You think you're one step ahead. We'll see. So your intuition looks correct so far because cosine starts at 0 with a slope of the tangent of 0. So my tangent point is here. But what happens the moment I start moving to the right of that graph? Think about what's happening. Think about what's relevant to derivatives that's happening. Yes, I like that hand motion that I'm seeing back there. So what does that mean about the derivative function? Doesn't go up. So you were all wrong. Nice try. Thought you were smart. And then I get to 0. But maybe you can follow what is happening here because you were close. Okay, let's turn the thing on and figure out what's actually happening. My guess is people would think if the derivative of sine is cos, then the derivative of cos is sine. But it's not. So what is it? Negative sine. Or shifted, but we see a lot of that repetition happening, right? So the simplest way to look at it is it's negative sine. So we were close. Our intuition was close, but not quite there. Okay? And I can map out all the rest of it. And that looks really easy, but it's not always that easy. It's not like for derivatives, you just flip the sines to cosines and we're done and we go home. No, it's not quite that easy. There are some tricky parts to this. And you also might think that's the easiest derivative there is. There's actually one that's even easier, which we'll do later in this unit. How could it be even easier? It's like the easiest thing in the world. You could teach a child to do it, sort of. Okay, so let's get to our actual lesson here. We're going to write down, we're going to look at a little bit of a new notation, by the way. Don't overthink it. And we're going to just write down what we noticed there so we have record of it, and then we're going to do some examples. So we already considered the graphs of sine and cosine. So we're going to write if y equals sine x, then y prime is cos x. Just watch for a minute. Don't write this down. This is something I've talked to a couple of you about already, but we think of this as just notation. It's actually not. There's something subtle to it. You don't really need to know this for this course, but if it ever comes up, if you take calculus in university, you may see this notation. This is actually considered to be an operator. And what that means is I can write this out like this. I can say d sine x by dx. So I'm taking the derivative of this function with respect to x. That's something we understand. Or you could see it as like d by dx of some function. You could see it that way as well. Okay? And some technology uses this notation. So it's actually an operator. And when we write dy by dx, we're saying derivative of y, a function, with respect to x. Like that's what we were saying. It's not just notation. At any rate, what's it equal to? It's equal to cos x. But more importantly, what if we do d sine u, where u is some other function, but we're taking the derivative with respect to x? This would be, whoops, not sine, cos u times the derivative of u. Does anybody recognize that? What is that called? No, not quite. Good guess, though. I mean, this could be du by dx, yes, if that's what you meant. Chain rule. That's chain rule. Remember when we said power of a function rule, chain rule, same thing? They're not actually. Power of a function rule is a specific example of chain rule. This is chain rule. Okay? You'll see that more probably as we go. So then what about if y equals cos x, y prime is negative sine, careful. So again, writing these down in this new notation. Something like that. Looks easy enough. Let's try a few. All right, so dy by dx. Derivative of sine is, oh, by the way, don't get those backwards. Wouldn't that be a disaster if on a test you got all of them backwards, you got the negative on the wrong one? So, I mean, you got to make sure you have it pretty solid that you have the right one. So the derivative of sine is cosine times the derivative of what's inside here, which is the angle, by the way. 3x is the angle, right? So times the derivative of the angle, which would just be 3. And we're going to do a little bit of like, how would we simplify? How would we rewrite this stuff today as well? Easy enough. Next. You can try this one if you think you're ready. I'm just going to leave the coefficient alone. Derivative of cosine is negative sine. Times the derivative of what's inside the angle. Derivative of 4x is 4. And of course, we can simplify this a little bit, so I'll pull out the negative. 8 times 4 is 32. Sine 4x. Is that okay? Yeah. Yeah. Like, could you pull the 8 out and kinda? But I mean, in this case, I don't know that you would just go straight to that, right? But absolutely, a coefficient constant like that could always be left out. All right, so we're going to get into some slightly more interesting ones here. I'm going to think of this as sine x to the 1/2, right? And now we're looking at power of a function rule again, which is just chain rule. But so how do we do that? Well, we're going to look at the exponent first. So I bring that out. Leave the function alone. You might want to watch if you're busy writing. Or you're trying to beat me, I don't know. Subtract 1 from the exponent. Multiply by the derivative of what's inside the brackets. Derivative of sine is cos. Do we follow that okay? Clean this up a little bit. Cos x is on top, 2 square root of sine x. Any questions? Again, this one's pretty straightforward. We're about to get to a trickier one. This is your only reminder that this notation with the exponent means this. Right? We all know that, but there's a little mind trick that gets played on us in this kind of a question. So we're going to try to make note of it and watch for it. So how would we do this one? We do the exponent. I bring the 5 out front. Subtract 1 from the exponent. Then multiply by the derivative of what's inside. Derivative of cos is negative sine. Put your pencil down and watch. People think there should be an exponent here. This is a common mistake because it looks like it's part of that function that you're taking the derivative of. See what I mean? Doesn't it kind of? But if you look at this, we know it doesn't. This would be y prime equals, I bring the 5 down, I get cos x to the 4. Now I can see it's just cos x in that bracket. So it's obviously just negative sine x. When you look at it this way, I think it's obvious. People get fooled looking at it this way. And they start adding exponents to this. If you have to write it out like that, do it. Why not? Off to the side or just rewrite it like that. Force yourself not to make that mistake. Because you make it even once. Okay? We clean this one up a little bit. Not really, but I can bring the negative out front. So negative 5 cos 4x sine x, something like that. Okay, any questions? Now we get into the good stuff. Everybody okay? I'm leaving a little bit of space because I'm going to write something over top of this. This is about as complex as we get. This has everything. This is the one that you need to be able to, like the hard one that you need to know how to do. We do exponents first. I take this 4, I bring it out front, 4 times 7, 28. Sine, subtract 1 from the exponent, angle doesn't change. Times the derivative of the trig function. Derivative of sine is cos. No exponent on that. Remember what we just talked about? Angle doesn't change. Now times the derivative of what's inside, which is 15x squared. So we start with the exponent. Then we do the trig. I think you should write this down. Then we do the angle. In that order. And it's harder. This is chain rule twice. We did power of a function rule, where we did here and here. But when we took the derivative of what's inside, we had to use the chain rule again on taking the derivative of the trig part and then the derivative of the angle. See what I mean? This is very easy to muck up. To miss one part of it or have exponents in the wrong place. Start with the exponent, then do the trig, then do the angle. Again, we can kind of clean this up. 15 times 28, I think is 420. X squared sine cubed 5, whoops. 5x cubed cos 5x cubed. You tell me. No, not in this case. Nothing useful. If you think you're ready, you can try that one. Think about it. 3 steps. Exponent, trig, angle. Exponent, trig, angle. Do each part separately in your head. How we doing? This is what I got for my first line. There's the trig part in blue. Brought the 6 down, multiplied by 10, decrease the exponent by 1. Everything else stayed the same. That didn't change. Again, some people do that. They change this to sign here. Right? That stays as is. Angle stays the same. Then I take the derivative of the trig part. Derivative of cos is negative sine. Angle stays the same. Then derivative of the angle. Then we can clean things up. Although not much. We're going to do a little bit of talking about different ways that we can simplify these things. Kind of like when we did this in Unit 2. Don't overthink it yet, but start to get used to it. We're going to look at a few little tricks, and you're going to want to ask, well, how do I know when I have to look for tricks and when I don't? I mean, that's part of the art, but like you'll see even today a little bit of when you might and when you might not. And part of it is also when you're doing the practice, some of the answers might be wonky, and that might help you figure out why. But I can common factor a 4 out of here, so that's typically something we would do. 4 times 60 is 240. I'll pull the negative out as well, so negative 240. And I don't think I can do much else with the rest of this. Obviously, when I have an expression, that I'm adding, I need brackets around that. I don't need brackets around that. Yeah. No, I took it up front. Which is generally speaking something we would do, right? Any other questions? Yeah.
Inside bracket, it was for like it's just a number. There's no x, it's just 0.
Like sine of pi by 2? Yeah, I mean that sine of pi by 2 is a number. Right? It's 1. So the derivative of that would be 0. Not just because the derivative of what's inside is 0, but that's a number. Sine of 3 is a number. Sine of 10 is a number. Right? That's something we could evaluate. So yeah, that would be a constant. Now we can determine derivative of tan from what we already know. How do you think we're going to do this? Anybody have an idea? Very nice. So sine over cos, and then notice that's going to be quotient rule. So let's do it. Does anybody remember quotient rule? Yeah. Okay, so the derivative of the top is cos times the bottom minus derivative of the bottom, which is negative sine, times the top over bottom squared. Can we do anything with that? What do you think? Daniel, what do you think? Okay, hold on. So cos x times cos x is cos squared x. That's what you're telling me? Okay, I'm okay with that. Oh, I got two negatives. And then sine times sine is sine squared x. Okay, I like that. But I think that's it, right? I don't see any way we could simplify that further. Right? What? Yes, it is. You're right. Pythagorean identity, very nice. Who would have thought that might happen? Whoa. Remember your we're not really doing identities in this. I mean, there's a little bit that comes up, but we're not doing a day on identities or anything like that. Sorry to disappoint you. I'm sure some of you are disappointed if you're good at them. But once in a while they come up. Once in a while we can use them in order to simplify, in order to solve more easily. This is also known as secant squared x, which you'll often see it written as. So we're going to write this out. So d tan u by dx is secant squared u times u prime. And again, this comes down to like, well, what are you doing with it? Do you want it in terms of sine and cos? Do you want it like, there's no universal answer to that question. What do you think, just guessing, cotangent might be? So the reciprocal? Not though. If you think about the quotient rule, the reciprocal wouldn't make sense. Like the reciprocal of a derivative wouldn't make sense to be the reciprocal of the function. Think about it more if you want to. It wouldn't make sense. Good guess though. It would be a common guess. Anybody else? Very close. Negative cosecant squared u prime. Kind of easy to remember because we had the negative already, so just remember that it's got a negative in it. I don't think that'll come up very much. All right, so we're going to do a couple more examples and then a bit of a different kind of question, and then we'll be done. You can do the first line of this one. There's no trick to it. Van, what'd you get? So I bring the exponent down, multiply by 4, I get 8. Subtract 1 from the exponent. That's just the exponent part. Now I'm doing the trig part. Done. I would not expect anybody to think of doing this. Couldn't I write this as 4 times 2 sine x cos x? Why would you want to? I don't know. Does anybody know what 2 sine x cos x is? So it's, of what though? What do I just write, double angle? Which way? Sine, very good. Teamwork. So sine 2x. I don't know why you'd want to do that. Like I said before, I think some of the answers in the practice do that. It's from a textbook, right? So you're going to do yours and you're going to be like, what? That mine's not even close to that. If you have x's and the answer has a 2x in it, some identity was used. You're not right. It's not just like simplifying with fractions that you're going to change the angle. So again, this is just good practice. Maybe you want to do it for some reason. Maybe you don't. I don't know. Don't overthink that, except for checking your answers. But again, like sine x plus sine x is not sine 2x. Oh my gosh. 2 sine x is not the same as sine 2x. But anyway, so sometimes we can do little tricks to do stuff like that. Let's try one with tan. That's not an exponent. So don't overthink this one. It was a long time ago. Does anybody remember what the derivative of tan is? Don't look at your pages. Zach? Say again? Yes, or I'm going to use secant squared x because we tend to, I don't know why, but yeah, very good. So secant squared of 5x times the derivative of what's inside. If you need brackets to make sure that you're clear about what's in the angle and what comes after it, use brackets. Okay. We would probably write this as 5 secant squared 5x. Then it's not ambiguous about where that 5 goes. Or maybe for some reason cos squared 5x. I don't know. Oh, and look at that. Cancel that out. Why are you laughing at me? Because that's absurd. Oh my gosh, don't ever do that. Don't ever do that. You can't cancel out into an angle in a trig function. That's something people might want to do. Okay, last one of these. Looks pretty simple. What's the point of this question? It's product rule. It looks just like all the ones we've done, but it's one of those sneaky product rules. Remember when we did implicit differentiation? And there's those sneaky ones like x times y. It looks like it's just so easy, but it turns out there's actually more to it. Still pretty simple, but same thing here. Derivative of the first thing is 1 times the second thing plus derivative of the second thing, which is secant squared x times the first thing. And generally speaking, we would write the x first, but there's not really anything else I don't think I can do here. Any questions? We've got a couple more that are a little bit different. Not like new stuff, but they will push us a little bit. We're all good? Who remembers how to find the equation of a line? All the way back to grade 9. So the formula that I like to use, remember this one? Y minus y1 equals m times x minus x1. What is the input for this formula? What do we need to use it? Slope and a point. Do we have slope? No. Do we have a point? No. We got to go find both. Think about that as your objectives, right? It's a little bit tricky because we got some more review to do. So I'm going to go ahead and find the point first. So I'm going to find y when x equals 5 pi over 6. I've got the x value of the point. I got to find the y value of the point. So cos of 5 pi by 6. Oh boy. How do we do that? Okay. So the answer is 30? Yeah, but that's a good start. Let's see if we can refresh our memory here. So 5 pi by 6 is in quadrant 2. Very good. And Emery told us that the related angle is pi by 6. We need to know that. We also need to know cast. What does cast tell me? Which quadrant they're positive and negative in. So cosine's negative in this quadrant, so it's going to be negative. What else do I need to know? Does anybody... The best way of doing this, folks, I think, memorize one of them. Cos of pi by 3. For some reason, this is the one that teachers always say to memorize. What's cos of pi by 3? Huh? No, that's just converting the angle to degrees. We need the result. The reason why this is useful, at least when I was a kid, is because calculators couldn't do fractions. So if you punch cos pi by 3 into your calculator, you get 0.5. So we know, and you can still check that. So you know it's a half. And then we just know what the other ones are, and by process of elimination, you can figure out what they are. That's the fast way of doing it. That's the efficient way of doing it. The slow way is 1, 2, root 3. The big angle is pi by 3. The small angle is pi by 6. Cosine of pi by 6 is adjacent over hypotenuse, so it is root 3 over 2, not 1/2. It's either 1/2. If this is too fast for you, you got to go and review MHF. Let me write this down first. We can go over it again more slowly, but we don't have time right now. So negative root 3 over 2. Yes? Do it without what? Without the x value? No, then you just have a function that's infinite points. How would you do it? No, we're trying to find the equation of a tangent line. Yeah. Okay. So that means my point is 5 pi by 6 and negative root 3 over 2. How in the world are we going to find the slope? Tricky question. Isabel, what do you think? It's calculus, folks. Of course we're going to take the derivative. We set it equals 0. Not in this case. That's usually what we do. Not in this case. Thank you. We're going to take the derivative, which is pretty trivial because it's just cos. So negative sign. And then find the value of the derivative at the point we're looking for. That's going to find us the slope. Oh, I should have said that. That's what we're doing. Slope. We don't usually put titles, but just because we're remembering this. Oh man, you got to learn all this new stuff and remember things from last semester. Life's not fair. So sine of 5 pi by 6. Well, sine is positive in that quadrant. If cosine was root 3 over 2, then sine is the other one. So it's a half. I already have the negative. So this is going to be negative sine of pi by 6, which we don't have to write that down anymore. We did in MHF, but now you can get straight to it. And quite frankly, your calculator can give you that too if you don't know how to do that. But once you kind of memorize them and once you practice a little bit more, it's probably faster just doing that than bothering to punch it into your calculator. Everybody okay? Okay. Now we're doing point slope formula where our slope is negative 1/2 and our point is 5 pi by 6. The only last thing we have to kind of review here in negative root 3 over 2, right? The only last thing that we have to do here is how we show our final answer. It's a little bit wonky. It's a little bit different. So I sub y in for y1. Sub the slope in. I'm going to multiply by 2 on both sides. I'm going to show it. I wouldn't usually, but this one time. expand through 2y. Am I going too fast? Are we okay? No answer? Too slow? Just for you, Emery, I'll rush through the rest. Okay, and then I'm going to move everything to one side. I like to keep my x's positive, just an old habit. And this is the one time where in standard form you're allowed to leave a fraction. We're not going to multiply through by 6. We can leave angles as fractions like that. Exact value, we do not put root 3's and 5 pi by 6's together and round. This is typically how we leave them, exact values. This is just good practice, really, right? We only got 6 minutes, but I want to do half of one more. It's a little bit harder. And then I'll let you finish the rest and you can check your answer online. Remember what we started with. The derivatives look so easy. The derivative of sine is cosine. The derivative of cos is negative sine. It looks so easy. But there's a bit more to it, especially when you get those questions that have 3 layers. They take some practice. So this one's a bit trickier just because it's got more going on. Sometimes an unfortunate mistake is people miss part of the equation just because of the way the question's written. So make sure you see that there's 2 parts to this equation. I'm going to take the derivative first. Again, we have to do exponent first. Then times the derivative of what's inside, or the derivative of the trig part, sorry. Then times the derivative of what's inside, but that's just 1 because it's just x. Happy with this? Okay. What was our point? Pi by 4? Yeah, pi by 4. F prime at pi by 4. Now we just have to find the slope and find the y value. Maybe I change this to 1 over cos squared of pi by 4. You don't have to, but you think of it that way maybe. Okay, so very quickly, our other special triangle. What is cos of pi by 4? Very nice, 1 over root 2. So I've got negative 2 times 1 over root 2. Sine of pi by 4 is the same, 1 over root 2. Plus 1 over root 2 squared. So that's root 2 squared. You okay with that? If you have to go back and think about this a little bit more slowly, I strongly suggest you do that. One over root 2 times 1 over root 2. Root 2 times root 2 is 2. So that's a half times negative 2 gives me negative 1. Root 2 squared is 2. Oh my gosh, look at that. I got a slope of 1. Go figure. You got to get the work done properly to get it simplify nicely, right? Again, you can just use a calculator for that. Find the y value, point south formula, put it in standard form. Any questions?